Welcome to this webinar on explaining models built in H2O-3. My name is Parul, and I am a principal data scientist here at H2O.ai. So in today's webinar, we'll start by talking a bit about H2O. We'll then cover the responsible AI aspects. We'll then talk about H2O-3, which is an open source library, in fact, open source distributed in-memory machine learning platform. We'll then use H2O-3 to train a machine learning model and then use the model explainability interface within H2O-3 to explain the predictions of the models. In case you have questions during the webinar, feel free to put them in the chat below and we'll try our best to answer them. And if we are not able to take up all the questions, we'll reach out after the webinar is over. So before we get started, let me tell you about an exciting event that is happening very soon in India, which is the H2O World India. So it's a Make AI in India and Make AI for the World. So for the first time ever, H2O World is coming to India. We've had events in the past in San Francisco, New York, London, Sydney, and other global locations. And now it's coming to Bengaluru, Karnataka on 19th of April. So whether you're just getting started with AI or you're a power user looking to expand your skill set, this is the right place for you. So if you want to register for the event, you can go to the site of H2O, and there you can just register for H2O India. We'll also be offering free passes to the community members soon, so please keep a lookout on our LinkedIn. And if you have any other queries regarding H2O World, don't hesitate to reach out to any of the H2O members. So let's start with H2O as a platform. Specifically, what is H2O Cloud? So H2O AI Cloud is an advanced AI platform that allows organizations to solve business problems quickly using AI. The idea is to enable the individuals such as data analysts and data scientists and developers to create world-class AI models and applications faster, with less time, more accurately, and thereby making AI accessible to the business users. So H2O AI Cloud is a name given to a platform that encompasses a few core components or the products of H2O, right from H2O driverless AI to H2O-3 to AI App Store, H2O Hydrogen Torch, H2O MLOps, and some other H2O package services. And together, that toolkit is known as H2O Cloud. Now let's talk about responsible machine learning. And as the name suggests, responsible machine learning means to use machine learning in a responsible way. So some of the core ideas of responsible AI that we practice at H2O is ensuring that our AI systems, they meet the relevant law and regulatory requirements. They are user-centric and they support the human-machine systems. There's a defined, well-maintained process for another individual or team to perform validation tests before your model goes to production. There's a response and escalation plan in case there's an issue in the production to fall back. Also, the AI system should be auditable, and there should be a defined owner for each stage in the life cycle. The models that you're creating are secure from external threats, they're resilient on ethical attacks, but they should also maintain privacy where required. These models or the systems should be able to provide intuition and understanding to humans why a model is making a particular prediction. And these end users need not necessarily be data scientists. They could be business users or people who do not have technical know-how of how machine learning works. And finally, to forecast and monitor the business ROI of AI projects, so the business impact should also be taken into account. So we've quickly covered the fact, but now let's come to the title of the webinar, which is explaining models built in H2O-3. And so what is H2O-3? So H2O-3, like I said before, is a fully open source distributed in-memory machine learning platform with linear scalability. Now, not only does it support the most widely used statistical and machine learning algorithms like XGBoost or GLMs or GAMs, it also has a dedicated toolkit for modern explainability. So you can easily train your models, and then you can easily visualize with a single line of code, and then you can assess the predictions of the models and make sure that they are what you expect it to be, and maybe not incorrect. And if you think there is something which doesn't fall in place, you might go back and try to debug your model. So I've been talking about this model explainability interface a lot. And so what this interface is actually, it's a simple function called H2O.explain. So you'll import H2O, and then you can just call on H2O.explain in case you want global explanations from your model. And in case you want local explanations, you can just write H2O.explain underscore row. So global explanations would be when you want the explanations for the complete model, right? So that's the complete explanations, like how your model sort of works. But in case you want explanations for every row of the data set, then we would want local explanations, and H2O-3 offers both of them. Now, the best part of using the model explainability interface is that there's a single function. It will automatically generate a list of explanations depending upon three important things. So what is the nature of the problem, whether it's a classification or a regression problem? What is the kind of explanation that you desire, whether it's global for the entire model or for a specific data point or local? And what is the nature of the models? So did you train a single model or you train an ensemble of models? So depending upon these 3 points, you are going to get a list of explanations. So overall, we have the following explanations which are generated for either a list of model or an AutoML object. So as you must be aware, H2O3 also has an AutoML object. So if you have more than one model, you also get a leaderboard, which compares the metrics across all models. You get a confusion matrix if you have a classification model, and you get a residual analysis in case you have a regression-only model. You also get variable importance or feature importance plots, depending upon whether you have stacked models or non-stacked models. You also get a model correlation heat map in case you have more than one model. So this compares all the models. Then you have one of the most commonly used explainability technique called SHAP. So SHAP summary plot, partial dependence plots, and individual conditional expectation plots. We're going to see them when we work with the code. So now it's time to start working with the H2O explainability toolkit. So the notebook that I'm using, the link to this has already been shared. It's a collab notebook, so you can easily code with me, or you can code at your own end. So this is the notebook explaining models built in H2O. And it's just all the things that I just discussed with you. So for example, what are some of the algorithms which are supported by H2O3? So we have generalized linear models, decision trees, generalized additive models or GAMs. So these sort of models like GLMs, decision trees, and GAMs are designed to be inherently interpretable. But other algorithms like gradient boosting trees and neural networks are black box in nature, and as a result, you have to use some post-hoc techniques to provide a way to explain the model predictions. You can also actually go to, I'll show you. So this is the documentation of H2O3. And in this documentation, you can see all the algorithms that is supported by it. For example, in supervised learning, these are the models which are supported in unsupervised. We support GLRM, isolation forest, K-means clustering. And then other than that, also we have word-to-vec, DF-IDF target encoding. And here, if you look, you have all the widely used models, XGBoost, uplift, distributed, uplift random forest, SVM, stacked ensembles, GBMs, CAMs. So this is all in the documentation, and all of them come with an example. So in case you want to try H2O3, you can use it. You can read the documentation, which is pretty robust and pretty detailed. So let's get back to our notebook. So we're going to start by setting up our environment, which means we're going to install H2O-3. So in Collab, the installation is very simple. You just need to pip install H2O-3 and it gets installed. But you can also download it from this official website, right? In case you want to work locally with it. So you can go to the link and download it. Next, we're going to import the necessary libraries. So, so for working with H2O-3, you don't need to import NumPy. This is just I've imported. But this is not important. You can just import H2O. And then from H2O estimators.estimates, I'm going to import H2O gradient boosting estimator because I'm going to use a trainer GBM model. So the seed is for reproducibility. And here it is. With H2.init, I'm going to initialize it. I can also give it a maximum memory size, but I can leave this. So remove all does remove any existing data structures from H2 memory. And H2.no progress is, I don't want to see the progress bars, but in case you want, you can leave that. So let's start by loading the data set. Now, we're using the Lending Club data set, which is a pretty famous data set, also available on Kaggle. So this is a collection of financial data, which is related to loans issued by Lending Club company. Here you have to identify whether a loan is bad loan or not, depending upon whether the person is going to return the loan. So I'm going to import the data set by simply calling h2o.import file. So I have a CSV file, but I can also call in a TSV and Excel files, right? So I have to pass in the path to the data set in case it's locally. So if you're using locally this data set from a local system, then you'll have to give that path. So let's run this cell. So once you run the H2O, you initialize H2O. So if you get a screen similar to this, which says server is running and connecting to H2O server successful, this means everything has been installed perfectly. And now you can use H2O. So you basically start a H2O cluster, right? And that's what this H2O.initialize does. Now I'm going to load the data set, and then I'm going to look at the top 10 rows, first 10 rows by calling the loans.head function. Now, if you are a Panda user, you'll see that the head command there only outputs the top 5 rows, but here we get first 10. So we can see here that there are 10 rows and there are 16 columns. So you have loan amounts, the term for which loan was given, the interest rate, home ownership, whether it's rent or owner, and so on. So this data set consists of a lot of predictor variables like loan amount, term, and interest rate. And there's also a target variable called the bad loan, right? So the target is 1 if the loan was bad and 0 otherwise. So this, as you can see, is a classic binary classification problem, right? The next step is to train a baseline gradient boosting machine model using H2O. So the first thing that I'll have to do is I have to make sure that my target column is encoded as a factor. So it's very simple to do in H2O-3. So I can just write loans, bad loan, dot as factor. By choosing as factor, I convert this target column or this specific column, I encode it as a factor. And let me see. So now I can quickly see with dot table that there are 32,000, more than 32,000 instances where loan is not bad, and there is just about 6,000 instances where the loan is bad. So this is also not a balanced, you could say, data set. We've already called seed before, so I don't think you need to call it again. Okay. So now what I'm going to do is I'm going to, because I just have a single data set, so I'm going to split this data into training, validation, and test set to evaluate the performance. So H2O has, we can use the H2O.split frame method, which splits it in the ratios that we defined. So here, train, validation, and test set is split in the ratio of 0.7 and 0.15, right? So for training, I want 70% of my data set. Next 15 I want for validation set, and the remaining, which is again 15%, would be used for testing. And so I'll ensure that this model never sees the test set, but it's only validated on the validation or tuned on the validation set. And let me quickly look at number of rows in each of training, validation, and test set. So everything looks good. Now I'm going to specify the input or the predictor, then the output or the response column. So my target is bad loan. I will now ignore the ID because ID has no signal from which the model can use the ID in any way. Also, I will remove the bad loan from the predictors. So when I remove all this, all my predictors will now not have the bad loan column as well as issue date or issue ID, and my target will be bad loan. So we've done all the pre-processing and everything, and I think now let's start by the phase that is going to start training the model. So we are training a GBM model, and so the seed should be what we actually first described. So we simply write gbm.train, we pass in the predictor, we pass in the target, and we pass both of the frames, and I'm just giving an ID. So that if I need to look at the model again, I can use the model ID for that. Now you can see it gives you a lot of things. In fact, it gives you a complete summary of your model. You can see your model metrics. So you see your model details here. So this is the model key, baseline GBM, which you specified as an ID. It says that there were number 50 trees, number of trees, number of internal trees, the model size in bytes, what is the minimum depth and maximum depth. So there's a whole lot of information. You can use this. It gives you model metrics, a confusion matrix, in other maximum matrices, expected threshold. So you can just go over them and just look at each one of them and see how can you understand your model better. It also gives you variable importance, saying that address state is most important, whereas verification status is least important for this specific model when trained on this specific data set. We can also check its performance on the test set now. So, and let's just sort of see how it's performing on the AUC on training, test, and validation sets. So we see on the test set is 0.69. On the validation side is 0.72. So it did overfit the training data. So you can sort of also, because this is just a baseline GBM, we've not sort of done any sort of feature engineering or not even tuned a model. So you can go ahead and tune the model. In fact, I've linked a resource for tuning. So there's this whole document which tells you how to tune the model and what does each of the parameters mean, where you can use this. But our motive for today is to explain the model explainability interface. So I'll leave this to you. You can go ahead and perform tuning or feature engineering to improve your results. Now let's go to the explanations for single models. So once your model has been trained, the next thing would be, and also evaluated on the held out data set, and it showed some decent performance. So I think the next step is to understand how the predictions are made and which features the model relies on most to make those predictions, right? And it's very simple. This just one. So we'll start with the global explanations first. So global explanation refer to the ability of the model to provide explanations for predictions at a global level, okay, rather than for individual inputs. So these explanations will apply to model as a whole, than just a specific input example. So this is why is global explanations important, because they help you understand and give an idea about the overall behavior of the model. So we'll just call gbm.explain, and let's say we are trying to see or explain the predictions on the test data set. And now we talked about 3 important points. So initially that how this works or what sort of explanations are generated. It depends upon the nature of the problem. So whether it's a classification regression problem, so it's a classification problem, so we get a confusion matrix, you can see here. And then also it depends upon the global and local nature. So we want a global explanation. So we just use .explain. And then also whether it's single or multiple models. So ours is a single model, right? But you can as well use this for multiple models. So this confusion matrix, as I think you all must be knowing, it shows predicted class versus the actual class and tallies the number of test set instances with each combination of actual and predicted outcomes, right? The next is the learning curve plot. So this gives you the loss function or metric dependent on number of iterations or trees for tree-based algorithms. So we are using a tree-based algorithms. So this shows the metric or the log loss with the number of trees. So how it affects first for training and validation set. And depending upon, this gives you an idea about whether the model overfits or not. So the orange line is the validation line and the blue is the training line, and the green one is actually the selected number of trees, the model that's selected. Next is the plot which is actually the first plot that we all generate after we train a model. It's the variable importance plot. So it shows the relative importance of the most important features of the model, which we also saw initially was address date, and then a term for which the loan was given, interest rate, and so on, right? Now, this is dependent upon the test data set. This might be different from the training set, but we are generating explanations on the test set. So all these inferences should be made with regards to the test set. The next plot is a SHAP summary plot, or SHAP is an acronym for Shapley Additive Explanations. And they provide a way to understand the contribution of each feature towards the prediction, right? So let's say if, let's just go back to the data set. So what SHAP does is it will tell you what is the marginal contribution of each of these features, say loan amount, term, interest rate, and so on, towards the prediction for this row. And so you'll get SHAP values for all of them. And the more the SHAP value, which means more the contribution. Now, you generally get local explanations for that. But when you can aggregate them, you also get these global explanations. So this is a little confusing at first, a SHAP summary plot, but what it's basically doing is it will show the contribution of features for each instance or row of data. So what these features, the SHAP summary plot does is it provides an overview of which features are more important to the model as compared to others. So now how do we get this SHAP summary plot is we plot the SHAP values of every feature. So the number of features you have, you calculate, the SHAP calculates the Shapley value for all those features, and then you plot them. So let's just sort of see what does this axis mean. So first, let's look at the y-axis. So the y-axis here, it denotes the features in order of their importance from top to bottom. So this is based on the Shapley value. So this means interest rate is most important, then verification status. So this feature importance is based upon the Shapley value, right? The horizontal location of these points. So how do you get this? It represents the feature's impact on the model's prediction for that particular sample. So each dot here or each point here basically represents each row of data. And this bar on the right basically shows the normalized feature values from a scale of 0 to 1. So it's 0 here and 1 here. Of course, the red one means higher value and blue means low value. So let's look at interest rate. And from here, we can see that all the sharp values, so this is the sharp value. I'll have to decrease the size further. Here. So we can say that as the interest rate increases, of course, like here. So firstly, from this plot, we can see that interest rate and term have a higher impact on predicting whether a person is going to default on the loan as compared to other features, right? So people who have a higher interest rate here. So if you look on the right-hand side, you see this red. Red means higher value. So this is people with high interest rate, and the blue is people with low interest rate. The people with high interest rate have a higher Shapley value. That means they have a higher chances of defaulting more as compared to people who have a low interest rate, right? So this is something or that we're getting from this plot by looking at the plot. Similarly, people who take loans for a higher term, you see the red one, they also have a higher chances of defaulting on the loan or higher chances of sort of getting a bad loan as compared to other. And so you have to look for each feature, and then you have to get back and try and understand if this is exactly the scenario, or this is as per what we think or what the domain experts think. So these are the plots that we got for, let's say, global explanations, right? And then we have partial dependence plots. So partial dependence plots will give a graphical depiction of a marginal effect of a variable on the predicted outcome. So how is your mean response or some average, or you could say mean target changing as you change feature, keeping all the other features constant. So what you do is you pick up a single feature. Let's say we picked up address state, or so address. Oh, okay, I think this is more visible here, right? So let's say we take interest rate. Now what we're going to do is we're going to sort of keep all the other features here. We're not going to change them, but we're going to vary interest rate, and then we're going to see how the mean response or mean target variable changes. So here you can see it as the value of interest rate sort of increases, right? From, let's say, 5 to about 24, the mean response also increases. So as your interest rate increases, the chances that you're going to default also increases. And this boundary basically on top and bottom is the confidence interval. So the average mean response here would be the average default rate. So it increases with the interest rate. But this very important thing that you can see from here, you can see the histogram at the back in the gray is the data, right? So you see here that at one point, after some time, at the end of this graph, there is no histogram. So this means here you don't have much data, right? So what I can infer from this graph is that for the interest rate plot, we can see that the average default rate increases with the interest rate, but then data becomes sparse for larger interest rates. And if we should rely on the graph here, it's something of a question, because here we don't have much data, and you sort of need data to make inference, but we don't have data. So this is an important point to remember. Especially when you can overlay your PDPs on your histograms, and you should also see where there's data. So the PDP will be more truthful where there is data, which you can see between 7.5 and 17.5, but is it necessarily truthful at the ends is a question. There's another important point for partial dependence plot. So because you created for single features, because the idea is to keep all the other features constant and you only take the feature of interest, it doesn't consider any interactions or correlations within other features of the model. So it's important to consider other factors that may affect the prediction when interpreting a partial dependence plot. So So what is the alternative to a PDP? Let's say if there are interactions. So for that, we're going to go for individual plotting functions, right? So right now we just use a single function, which will automatically populated a number of explanations by gbm.explain. Now we can also choose to only output specific functions. So let's say I just want a feature importance plot. That's all. I don't want any other plot. So I can just write gbm.var_plot. So I only get a single plot. If I only want a sharp summary plot, I can just say gbm.sharp summary plot, and I'll get the same plot that I used before, but I'll only get this plot. Similarly, you can get a partial dependence plot, let's say for interest rate. So instead of getting a whole lot of information that I don't need, I can specify which feature I want the partial dependence plot for. And there's a nice plot. So remember, I told you that partial dependence plot do not consider the interactions or correlations within other features. So for that, you can use an ICE plot or individual conditional expectation plot. So what that plot does is, ideally, if I'll show you, so this is a PDP for, PDP is the short form for partial dependence plot for interest rate, and this is a nice plot for partial dependence plot. So here in partial dependence plot, you will only see an average line. So this is the average line, right? So average of all the values of interest rate when you sort of, but here you see all the individual lines, and you can decide. So for every percentile you see. And now you see that while some of them do increase, the response is increasing, or the probability of defaulting increases with increase in interest rate. For some of them, it decreases first and then increases. And for some of them, it's constant. So you see some different scenarios when you look at in much granular detail. So an ICE plot is pretty similar to a PDP plot because both are visualizing the relationship between a predicted outcome and individual features in a data set. But the main difference here is that ICE plot will show how the predicted outcome changes as the value of a particular feature changes, right? While holding all the other features constant. But what partial dependence plots show is the average predicted outcome. So they show the average predicted outcome. And because of that, you just have an average or a single line. While this is the ICE plot for interest rate for different percentiles or deciles here. As you can see, it's for 0th percentile, 10, 20, 30, 40. So this gives you more granular picture, right? And also you can sort of see if there are interactions. So if there are points, places where your ICE plot and your partial dependence plot, they diverge, maybe there are correlations or interactions in input variables, and that's something to watch out before you put your models into production. We also can, so right now we were just looking at global explanation. So the average, you could say, behavior of the model, but we can also look at local explanation. Let's say if I'm only interested in a single row, right? I'm not interested in the entire model, but a single row. So let's say I can explain the row index 50. And so when I do that, all I get is, I'll only get for that specific row. So I get a sharp explanation for that on row 50. I also get an IC plot for that 50, you can see here. So it's the same way you're going to interpret this, but now this is not what the entire model is telling me. This is for that specific 50th row. And then you can close the H2O cluster when you're done with it. So you can just put H2O cluster. And so the session is closed. So so this was the entire walkthrough we did. We looked at the model explainability interface. We discussed the importance of explainability in machine learning, right? We saw the responsible AI picture, or you could say in the slide, in the preceding slide, we saw why responsible AI is very, very important, especially when you're using it in high-stake decisions. Then we used H2O's dedicated toolkit for model explainability to visualize and assess trained GPM models prediction. We then derived the global as well as local explanations. And so while this article basically, while this webinar was dedicated to understanding single models, we can also use the same thing for multiple models. And you can go to the website and the documentation to understand how you can also explain scenarios where you train multiple models, ensemble of models, or if you're using H2O AutoML. So as I said, I will share the code and the notebook. And in case you have any questions, even afterwards, feel free to comment and reach out. So that's for today. Thank you so much and hope you had a nice time. Thank you.